Now, is that ball coming back or not? Looks funny, doesn't it? But that's the way things could be if there was no gravitational force to hold things to the Earth's surface. In this lesson, you will learn about the universal law of gravitation, gravitational force, and its effect on a freely falling body. At the end of this lesson, you will be able to explain gravitation, state the universal law of gravitation and explain its significance, derive the expression for gravitational force between the Earth and an object on the Earth's surface, calculate the acceleration due to the gravity on Earth, differentiate between mass and weight, and compare the weight of an object on the Moon with its weight on Earth. When an apple fell on Newton's head, he figured out that the Earth exerts a force of attraction on all bodies near its surface. The force of attraction exerted by the Earth on any other body is called gravity. Gravity is what brings things down again when we throw them up. Like Earth, all bodies in the universe attract each other. The force with which all bodies in the universe attract each other is called gravitational force. The revolution of the Moon around the Earth is also a result of gravitational force, which acts towards the center of the Earth. Such a force exerted on a body moving in a circular path that acts towards the center of the circular path is known as centripetal force. Newton originally thought that like an apple or a ball, all objects should fall to Earth. However, based on his study of centripetal forces, he was able to explain why this does not happen. When a body A is in circular motion around another body B, it experiences a force directed away from the center of the circular path, which is equal in magnitude and opposite in direction to the centripetal force. This prevents the two bodies from moving towards each other due to gravitational force of attraction between them. This is the reason that the Moon and the planets revolve in their respective orbits instead of falling on each other. For a better understanding of centripetal force, let's observe a game of hammer throw, an Olympic athletic event. Each thrower swings a hammer around and releases it at a point such that the hammer flies off in one direction. You can observe that the hammer gradually gains velocity as the thrower swings it around, and the hammer flies off in a straight line which is tangent to the circular path of its revolution. While the athlete is swinging the hammer, that is, the hammer is in revolution, its direction of motion and hence its velocity changes continuously. This change in velocity produces acceleration on the hammer. This acceleration is directed towards the center of its circular path. Acceleration directed towards the center results in a force directed towards the center. This force is called the centripetal force, which means a center-seeking force. The reason for the motion of the Moon around the Earth is similar to that of the motion of the hammer just discussed. The gravitational force of attraction between the Earth and the Moon provides a centripetal force for the Moon. In the absence of centripetal force, the Moon would follow a tangential path similar to that observed in the case of the hammer discussed. In that case, our Moon would have flown away from the Earth long back. Consider the force that holds things to Earth, the occurrence of tides due to the motion of the Moon and the Sun, the revolution of the Moon around the Earth, and the motion of planets around the Sun. What do you think is common among all these phenomena? Nothing, you may say. However, through the universal law of gravitation, Newton explained the relationship between several such phenomena that were earlier thought to be unrelated. Newton's universal law of gravitation states that every object in the universe attracts every other object with a gravitational force, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The gravitational force acts along the line joining the centers of the two bodies. The law is universal since it is applicable to all objects, regardless of their masses or their positions in the universe. To derive the expression for the universal law of gravitation, consider two spherical bodies. Let m1 be the mass of the first body, m2 be the mass of the second body, r be the distance between the centers of the two bodies, which is generally referred to as the distance between the bodies. F be the force of attraction between the two bodies. According to Newton's universal law of gravitation, gravitational force between two bodies, F, is directly proportional to the product of masses of both the bodies, m1 and m2, and inversely proportional to the square of the distance between them, r. By combining both these relationships, we get the gravitational force between the bodies as F proportional to m1 m2 divided by r square. To equate this relationship, we use a constant of proportionality, g, which is the universal gravitational constant. This gives us F is equal to g m1 m2 divided by r square. If m1 and m2 each equals 1 kilogram and r equals 1 meter, you get F is equal to g. Thus, the universal gravitational constant is numerically equal to the gravitational force between two bodies, each possessing a unit mass, separated by a unit distance. The SI unit of the universal gravitational constant is Newton meter square per kilogram square. Henry Cavendish found the value of G with the help of a sensitive balance. G equals 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. In deriving the expression for the gravitational force of attraction between two bodies, Newton used Kepler's third law of planetary motion. This helped him conclude the second part of the relationship known as Newton's inverse square rule. This rule states that the gravitational force F between two bodies is inversely proportional to the square of the distance between them. In deriving the inverse square law, Newton assumed that the planetary orbits are circular. If a planet revolves around the Sun in a circular orbit of radius r with a velocity v, also referred to as the orbital velocity of the planet, then the force on the planet is F proportional to v squared divided by r. Let's call this equation 1. the orbital velocity of the planet, v is equal to 2 pi r divided by t, where t is the orbital period of the planet. Squaring both the sides and simplifying, we get equation 2. V square is equal to 4 pi square r cube divided by rt square. Substituting equation 2 in equation 1 and simplifying, we get equation 3. In equation 3, 4 pi square is a constant. According to Kepler's third law, r cube divided by t square is also constant. Therefore, we can eliminate these constants from the relationship. Eliminating the constants, we get the relationship as F proportional to 1 divided by r square. Newton extrapolated these findings to all the bodies in the universe. Therefore, the gravitational force F is inversely proportional to the square of the distance between the two bodies. As we mentioned before, when you throw an object up, it comes down due to gravity. Thus, when an object such as this boulder is pushed or thrown from a height, it falls to the earth. Such an object is said to be in free fall. An object is in free fall when it falls to the earth under the sole influence of gravity. A fruit falling off a tree or a sandbag thrown off a hot air balloon hurtled towards the earth in a free fall. However, a parachutist descending from an aircraft is not in free fall, since he uses the parachute to counter the gravitational force of Earth. A freely falling body is always under the influence of the gravitational field of the Earth. But not all the bodies under the influence of the gravitational field of the Earth are freely falling bodies. A body under the influence of Earth's gravitational field can be a body dropped from a certain height, like a ripe fruit falling off a tree. A body projected vertically downward from a certain height with some velocity, such as a ball thrown down by a boy from the 5th floor of a building. Or a body projected vertically upward, for example, a stone thrown vertically upwards. Objects in free fall move only in one direction. However, their velocity changes as they fall. A change in velocity results in acceleration. The acceleration of a freely falling body due to the gravitational force of the Earth is known as acceleration due to gravity. Acceleration due to gravity is denoted by the small letter g and is measured in meter per second square. How can you determine how long it will take an object in free fall to reach the Earth from a specific height? To perform such calculations, you need to know the value of acceleration due to gravity. So, let us now derive the expression for acceleration due to gravity g. Consider a freely falling object of mass m. Let the capital letter M denote the mass of Earth. D be the distance between the free-falling object and the center of the Earth. And R be the radius of Earth. Since the object is in free fall, the gravitational force F on the object is the product of its mass m and acceleration due to gravity g. Let's call this equation 1. The gravitational force F between the Earth and the free-falling body can also be calculated using Newton's universal law of gravitation. F is equal to g into m divided by d square. When the object is near to or on the surface of the Earth, the distance d is taken as equal to the radius of the Earth r. Let this be equation 2. By equating 1 and 2, we can calculate the acceleration due to gravity as g is equal to g multiplied by m divided by r square. Since the Earth is not a perfect sphere, its radius is maximum at the equator and minimum at the poles. Hence, the acceleration due to gravity is greater at the poles than at the equator. However, this difference is negligible for bodies on Earth. To calculate the value of acceleration due to gravity g, we need to substitute the values of universal gravitational constant g, mass of the Earth m, and radius of the Earth r in the expression we derived. On substituting and simplifying, we find the value of g is approximately 9.8 meter per second square. Acceleration due to gravity at a place on Earth is the same for all bodies, irrespective of their masses. Let's use two identical objects with different masses to verify this statement. Drop a metallic ball and an identical wooden ball from a height. Do you notice that both reach the surface of the Earth simultaneously? Since the mass of the metallic ball is greater than that of the wooden ball, the force of gravity on the metallic ball is greater than that on the wooden ball. However, it doesn't seem to make the metallic ball fall faster than the wooden ball. This proves that acceleration due to gravity on Earth is the same for all bodies irrespective of their masses. In your study of motion, you have learned about the equations of motion. There are three equations of motion. 1. V is equal to u plus at. 2. S is equal to ut plus half at square. And 3. V square is equal to u square plus 2as. These equations relate displacement, velocity, and the acceleration of a body. The acceleration of all freely falling bodies is due to gravity. Therefore, we can simplify these equations for freely falling bodies. Now let us observe how these equations of motion are modified for freely falling bodies in all three cases. The first one is the case where a body drops from a certain height. Here, the initial velocity of the body u is 0. The acceleration of the body a is the acceleration due to gravity g. This value is positive because the velocity of the body increases as the body descends. Let's consider how the three equations change in this situation. Our first equation is v is equal to gt, where v is the velocity of the dropped body at the end of t seconds. Similarly, the second equation becomes h is equal to half gt square, where h is the distance covered by the dropped body at the end of t seconds. The third equation becomes v square is equal to 2gh, where v is the velocity attained by the dropped body at the moment it covers distance h. In the second case, we consider a body projected vertically downward with some initial velocity. In this case, the initial velocity of the body is not 0. The acceleration a is again the acceleration due to gravity g. By substituting a is equal to g in the three equations, we get the revised equations as shown. Acceleration due to gravity is positive in this case, as well as the velocity of the body increases downwards. However, in the third case, the body is projected vertically upward. In such a scenario, the velocity of the body decreases as the body ascends. Therefore, the acceleration of the body becomes negative. By substituting A is equal to minus g in the three equations, we get the revised equations as shown. How much do you weigh? 60 kilograms? 80 kilograms? What we popularly refer to weight is actually mass. So, what's the difference? How can you gauge your real weight? Mass is the amount of matter contained in a body, while weight is the force with which a body is pulled towards the center of the earth. Thus, weight is the product of mass and acceleration due to gravity, that is, W is equal to mg. The value of g is approximately 10 meters per second square. Thus, if your bathroom scales show a reading of 60, your weight is 60 multiplied by 10, that is 600 Newton. Mass is a scalar quantity, hence it can never be zero. However, weight is a vector that can be zero when the acceleration due to gravity is zero, for example in space. In the SI system, mass is quantified in kilogram, while the unit of weight is Newton. A physical balance is used to measure the mass of a body. Weight is generally measured using a spring balance. The mass of a body is universal, meaning it remains the same throughout the universe. The weight of a body varies from place to place depending upon the gravitational force on the body at that place. This means that your mass on the Earth and on the Moon would be the same, but your weight would differ, because the acceleration due to gravity on the Moon is different from that on Earth. The gravitational force of the Moon is far less than that of the Earth. That's why, before cosmonauts fly on a mission to the Moon, they are acclimatized in a simulated lunar environment. This is to ensure that when they land on the Moon, they are able to move around easily even though the gravity is reduced. Because of this difference in gravity, the weight of a cosmonaut on the Moon differs from his weight on Earth. Let's find out how much this difference is. The mass of the Moon is 7.35 into 10 raised to the power 22 kilograms, and its radius is 1.74 into 10 raised to the power 6 meters. The mass of Earth is 5.97 into 10 raised to the power 24 kilograms, and its radius is 6.37 into 10 raised to the power 6 meters. Using the universal law of gravitation, we can find the force or weight of an object of mass m on Earth and the Moon. By substituting the values and solving, we get the weight of the object on the Moon as 2.43 into 10 raised to the power 10 into g into m. Similarly, we get the weight of the object on Earth as 1.47 into 10 raised to the power 11 into g into m. By comparing these results, we can determine the relationship between the weight of an object on the Earth and the Moon. Thus, the weight of an object on the Moon would be approximately 1/6 of its weight on Earth. For example, if the cosmonaut weighs 600 Newton on Earth, he would weigh approximately 100 Newton when he lands on the Moon. This brings us to the end of this lesson on the universal law of gravitation. In this lesson, you have learned about gravitational force, universal law of gravitation, free fall, and acceleration due to gravity. The following section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.